I need to understand from you, this right here is called an exponential function. This is a new one. We haven't talked about this one yet. You talked about it in Algebra 2 or Algebra 1 for sure, but it's been a while. We have done the blue one before. I need to understand if you can see the difference between those. Do you see a difference between those equations? What about the exponent? Okay. So we have what's called a base and an exponent. The difference is that the exponent, you got to listen to this. You can't just keep talking over me. The exponent is a variable, and the base is a fixed number. A fixed number. Now that wasn't true of the parabola, the parabola. We had x squared, the quadratic function, and it had a variable base and a fixed exponent. I'll let you get that copy down here before I move on. Okay. Let's start off with 2 squared. If I plug in a 2 into that function, what do I get? If I plug in a 2 to the second power, what do I get? I get 4, right? What about 2 to the first power? 2. Now, it has come to my attention that the next one causes a little bit of confusion. So, let me explain what's going to happen with 2 to the 0 before I have a lot of you give me unusual answers. Some of you might already know the answer to that, but let me explain it. So, what is 2 to the third over 2 to the third? Isn't that 8 divided by 8? What do we know that equals? 1, right? Anything divided by itself is 1. Now, what are we allowed to do with these two exponents when we're dividing like bases? Subtract them. So what is 3 minus 3? That is 0, right? So we just proved this. So if I tell you, or if I ask you, what is 2 to the 0, you're going to tell me what? It's 1. But there's so many people that want to say that that's 0. And it's not 0. In fact, anything to the 0 power is equal to 1. You can do that with any base. Now, don't try to sit there and say to me, oh, but Mr. Stave, what about 0 to the 0? Is that equal to 1? No, don't try to trick me with that one, okay? I understand there is one exception to that whole policy. But anything else raised to the 0 power is equal to the whole number 1. Now, we do know what's going to happen with the next one because we talked about it last semester or last chapter. What is 2 to the negative first? 2 to the negative first. What happens to the 2 when you raise it to the 0? 2 over 1 is what it is right now. It's 2 over 1, and we're raising it to the negative first power. What happens to it? No, good try. Thank you for trying. Flip. We use the word flip. Right? So the flip is 1/2. Right. What about 2 to the negative second? 2 to the negative second. Now, I remember last chapter when I talked to you, I drew a really bad diagram of a tree, and I talked to you about the root and the power and the flip, right? The root and the power, and then we did the flip last. I do not see a root in this. What I do see is a power and a flip. But I definitely don't see any kind of cube root, square root, fourth root, or anything like that. So what do you get? Inside here you get 4, right? But 4 to the negative first is what? If you said it and I didn't hear it, that's 1/4. If that's what you said, sorry, I apologize. Okay. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, that was a bad one. 8, 9, and 10. Let me count them, make sure I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There you go. Gotcha. Those are all strikeouts, folks. For you. Okay. Now, I need you to focus on these y values, and I need to find out if you see something that's in common to all of them. Well, I think one of the things that they all have in common is that they are all powers of 2. That's one good thing. What else do you notice about all of them? They're all positive. Thank you very, very much. All right. Now let's think about this. If you went to this side and you put in a 3, what is 2 to the third? 8. 2 to the fourth would be 16. So you can see that this side's getting bigger and bigger and bigger. These are positive numbers. What happens over here if I put in a negative 3? Yeah, what is it? 1/8. What if I plug in a negative 4? 1/16. 1/32, 1/64, 1/128, 1 over 256. But guess what? They're all positive. Every single one of them. What? There's a calendar right behind you in the corner by the flag. Those are start times. I never put the end time of the period because it's math class. Right? We got to subtract. Okay, so all right, now listen. We're getting closer and closer and closer and closer and closer and closer to what line? What line are you getting closer to over here? 1/8, 1/16, 1/32, 1/64, 1/2. As it just keeps getting. It's getting closer to 0, isn't it? But it's never going to reach 0, no matter what number you plug in that way. 2 to the negative 1/1,000,000th power is not going to equal 0. Now, there's a story that kind of goes along with this. Suppose I take the distance between me and that wall, and I cut it in half, and I step forward. And then I do it again. And then I do it again. And then I do it again. Do you realize that I will never, ever, ever, ever reach this wall? So if you're always cutting it in half, you're never going to get there. Will you be close? Yeah. Yes, but you'll never get there. Because it's always half, 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 half. Okay? So on the one side of this graph, what we're going to see is if let's suppose that this table is the y-axis or the x-axis, what we're going to see is it's coming down, 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 down. It's slowing down, but it will never, ever touch that. Now, there is a song that was, I think, in the 1990s that was sung about these lines, which we'll talk about in a minute. But there is a song about these things. Okay, So we'll get to that in a second. Let's take a look at the graph, and then we'll talk about the name of that cool line here. Which one of these pictures do you think represents what's going on? As you put in bigger x values, you get bigger and bigger numbers. We'll take a look at D since you brought that up and see if that's right. Okay, so 2 to the 0 was 1. Yeah, that works. 2 to the first is 2. Yeah, that works. 2 to the second is 4. Yeah, that works. Yeah, I think you got the right one. 2 to the negative 1 is half. Yeah. And then we got a 1 smaller than that. Yeah, you got the right one. This is the one. Do you want your money to do this? No. Yeah. As we go forward in time, would you want your money to do this? Yes.
Oh yeah, go off.
Okay, we're going this way. Time marches on. Okay, I know what he's getting at. There's a story. There's a story about doubling your money every day, and yes, after 30 days, you're actually at 10 million. You start with a penny. Start with 1 penny, you double it every day, you continue to add them up, and you will have over $10 million in 30 days. But, yes, what are you going to do? I built my entire profession on that. Now, those people are called actors. Those are professional liars. Okay? Now, so do you want your money to do this? Yes. Yeah, I would too. Now, if you could consistently do this, which is doubling your money every year, and you were smart enough to leave your money in and put more in if you wanted to, right? Okay, then you and I would be buying our own private islands, right? Okay, this isn't consistent, and this isn't something you can normally do. But if you could, yeah, you're that's what you want. Do you want the coronavirus to do this? Yeah, not really.
Yeah.
Some people need it.
You know one of the most popular searches right now on the internet?
Do I have
Does Corona beer cause the coronavirus?
Yes.
No, I bet.
I don't know. Okay. I mean, there's a town in Indiana called Corona, Indiana.
Hey, you know what's actually in Indiana now?
I did hear that too. I don't know.
Northern Indiana.
Okay. So you do not want this to happen in some situations, but you would like it to happen in others. Okay? I need to know the domain of this function. I need to know the domain. Remember we talked about pushing the whole graph down on the x-axis? Tell me how much of the x-axis would be covered. Yeah. How much of the x-axis would be covered if I dropped that whole thing down? All of it, right? So you can say something like all reals. If you're familiar with the all real number sign, you can use that R with a double bar, okay? Which incidentally, whenever they need my assistance, I mean the government, they put that symbol up in the sky. I see that, I know they need me. Exactly. Okay? If you also put negative infinity to infinity, like that, I would accept that as well. Now, remember we talked a little bit about that line that it gets closer and closer to, but never touches? In this case, that line is running right through here, and that line is y equals 0. Okay? You told me it was never going to get to 0. It would always be positive. Okay? The cool name that we have for this line, asymptotes. And yes, folks, we get a lot of jokes out of that because you never, ever, ever touch the asymptotes. Spoken like a guy that gets punched a lot. You know what I'm saying? Okay.
So put the
Never ever. Yes, I do need to put that one on a shirt. Okay. Now, the song that was sung in the 1990s about this was sung by MC Hammer. Can't touch this. That's all about never touching the asymptotes. Okay. Got to go back and look at the lyrics, folks, if you really want to see that.
Sing it for him?
I could. I don't have the time right now. But I could. Okay. Put that in my next video.
Yeah, you definitely.
Okay. How about the range? Remember we talked about the range. That's where you push all the points up against the y-axis. Don't tell me all real numbers. That's not true, folks. Think about it. Squish the whole thing together on the y-axis. How much of the y-axis gets covered? It's going to cover a lot of it, but it's not going to cover everything for sure. What kind of numbers will it not cover? What kind of numbers would never be covered by any point if you squished it all up against the y-axis? Come on, look at that picture. Which 0 definitely not would not be in there. Yes. What else? Negative numbers. So what does that leave me with? What does that leave me with? Yeah. Now, Mr. Wilson, this is what you just said. Tell me what would be wrong if I did this. Yes, which means I touched the asymptote. No, don't do it. Do not do it, folks. Take that away because you will lose credit if you are touching. Thanks very much. If you're gonna tell me that it touches the asymptote, you're gonna lose. Yes, yes. Okay. Especially, yeah. Well, if you're 18 and they're under 18, really, seriously. Yeah. It's called like a offender list, you know. Okay. I need to know if. Well, before I do that, I want to show you one thing here. The most generic form of any. Stay with me. We'll get through example 2, that's question 2, that's the only one we're going to be able to get through. This is the most generic form of an exponential function. I need you to write that down. I also need you to understand that this number in the front on a graph represents the y-intercept. Now, the first graph that we did was y equals 2 to the x power. Can you tell me what number is sitting right here in front of that 2? It was a 1. Now, we never wrote it down, but we knew that it was a 1. And guess what? When we graphed it, you saw that it crossed right through there at the y-intercept 1. Right there. We had the y-intercept at 1. Yes, stay with me, please, even as you are getting ready. Is this in question 2? Can you look inside those parentheses and tell me whether you think this is going to be what we call growth, like the last example? No, this is going to be different, isn't it? Okay? This is actually called exponential decay. And the reason, okay, write it down. Stop talking, write it down. The reason it is called exponential decay is because the b value, which another name for that you should have written down is, we'll lock it in. Some of you are acting like you're done here. Growth factor. The growth factor, if the growth factor is between 0 and 1, what kind of numbers are between 0 and 1? Decimals, right? Fractions, decimals, those kind of things. Okay. If you have a growth factor that's between 0 and 1, then it's going to come down, 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 down. Is that what you want your money to do? Is that what you want the coronavirus to do? Yes. Yes, we do. Okay? Is exponential decay what your current car is doing? Your daily car that you drive to work, you drive to school, is it going down in value every year? Yes, because it's sitting outside and it's getting rained on and it's exposed to the elements, the salt, the rust. You're driving it, putting more miles on it, decaying all the parts in the engine. Now, I do realize that there are certain cars, after a certain amount of time, if they've been taken care of really well and not driven a lot, yes, they can go up in value. But the majority of our cars are doing exactly something like this. They are going down in value all the time, which is why they're not great investments. We called this one exponential growth. I should write that down. Where should I write that? We called this one exponential growth. Why do we think we called it growth? Because this number was bigger than 1. Bigger than 1. If it's bigger than 1, it's going to be growing. If it's smaller than 1, it's going to be decaying. All right, let's take a look at this example. What do we get when we take 1/3 to the 0 power? No, we do not. We get a 1, thank you very much. Anything to the 0 power is 1. We already talked about that. How about 1/3 to the 1st power? That's just 1/3, right? How about 1/3 to the 2nd power? Nope. 1/3 times 1/3 is 1/9, right? Because that's all you're doing is 1/3 times 1/3. Okay? How about 1/3 to the -1st? Ah, that's flipping it over. That becomes a 3. And then, yes, that would be 9 if you... Which one of those graphs? Why are A and C ridiculous options?
Because you said ridiculous. I feel like D is the answer.
You're right. You're right. I heard it, Mr. Glancy. You talked about it. Okay. You see a lot of negative Y values in there, right? Which means they never listened to MC Hammer. Because they did what? They touched the asymptote, right? They crossed right through it. Okay, now, we need to have a Y-intercept of 1. Does this have a Y-intercept of 1? We said that if you plug in -1, you get 3. Is this equal to 3? That ain't it. The answer is D, correct. Now, before you pack up, I want to know something. What's the domain of this function? That is another all-real situation. So, are you telling me that whether you are dealing with exponential growth or decay, you're always, listen, do you always get the same domain?
No.
Yeah, you do. It doesn't matter whether it's going down or going up. What about the range? It is the same as well. All the Y values greater than 0. Now, it's a big difference between those two because obviously this is not what you want your money to do. We're going to do a lot more with these functions next week. I mean tomorrow. I keep feeling like it's a Friday. I wish it was Friday. But we will do next week too.
Why is she